everyone. Thanks for joining us today. Another professional development seminar. Today's presentation is on rehabilitation of 34,000 feet of water main using pipe bursting. It's my honor to introduce Mr. Brian Gastrock as our presenter today. Mr. Gastrock is a professional civil engineer with more than 18 years of experience working on condition assessment, design, and construction management projects. Thanks for joining us today.
Thank you. So thank you for having me. I had originally scheduled this in the fall, and there was a scheduling conflict, so I got pushed to this year, which has actually worked out better for me. So I was, as normal, kind of mad dash putting this together in the last week, getting some of the last of the photos. So it gave me an opportunity to pull some better photos together that I didn't have. So with that, this presentation, those of you that know pipe bursting, the first few slides are going to be maybe a little monotonous. Maybe you've seen some of the information before, but then it's also going to present a case study on two of the projects that I worked on in the last year and a half or so. Kind of disclaimer, this is not promoting contractor technology, method, equipment, etc. There's a lot of stuff out there that we're not covering. Try to kind of focus it on what's available and being used in Alaska. And not all the photos here. I grabbed a lot of screen grabs from the internet, so when you see some of that stuff, it's not all Kaufman represented images. So quickly, the pipe bursting overview. So what it is you take, when you type pipe burst, a lot of times if you Google it, you find a burst water main, and you have geysers of water. Well, pipe bursting is a trenchless technology that replaces the existing pipe in place with a new product pipe. This is the one technology that actually increases your pipe capacity, and I'll get to that in a minute here on the next slide. But you have to use, it's always used on a fracturable pipe, and it started out with AC and clay pipe, old fracturable, standard kind of pipe. Cast iron is being used on now. Unreinforced concrete, as soon as you put reinforcement in there, it becomes much more challenging, if not impossible, depending on the type of concrete pipe. Ductile and HDPE. They're using it. It's a stronger pipe. It takes a different type of method. It's just a higher risk. And then also in the newer version of the Good Practices Manual, they're saying that they're starting to use it on some CMP. I've not seen that, but it's, again, it's still kind of relatively new. So quick background. This is a technology that's been around since the 70s. Hit or miss on the success rates back in the 70s. But then in the 80s, it became patented by companies in Europe, and they started to gain real traction with it and realized how viable it actually was and how useful it can be. It's always evolving. This is something that what I show here in 2 or 3 years, the slides may or may not be, they'll be trumped by something else that's happening. It started with the wastewater side. So typically where it started, this is the only trenchless technology where you actually, like I said, increase the capacity. So in an existing developed area, this is real popular. This is, again, why it kind of started in Europe. In a densely populated area, all of a sudden they put it out high rise, and your wastewater collection system is not sized to, your old 8-inch cannot convey the flows that you're seeing with this new 10-story high rise. So downtown urban areas, which is where this really became into effect. And so they started with the wastewater system first, taking an 8 or a 10 or a 12-inch old clay or brick pipe and using it, being able to burst it and upsizing it with a new plastic pipe to 12, 18, 24-inch. That's where it started. And again, this is a rehabilitation, and it uses the existing line and grade. So if you had a good straight sewer pipe, you could pipe burst it, upsize the capacity, redo your service connections if you needed to, but minimize your excavations, especially in a downtown, urban area where you're crossing through Main Street. You don't want to be doing that if you can avoid it. They're also using it as it's grown since the 80s. They're using it for size on size a lot of times. So you've got this old pipe that may be 50 or 100 years old clay pipe, and it's exceeded the life expectancy, or old AC pipe. But you don't need to increase the capacity, but you want to pull in new plastic pipe or cast iron that's old, rotted out, it's rusted out. So you're going to replace it with a plastic pipe. So they're doing it for size on size, as well as they're upsizing quite a bit too. So kind of the applications that it's used on, we talked about it being sewer. Water is really gaining popularity, especially in the state of Alaska. It's been used quite a bit there, not as much on the sewer side. They're using it now on services. There's been technology, I'll talk in a bit here about a new manufacturer that's kind of downsized their stuff and able to use it on small sewer services and water services, and they're using pipe splitting. Low pressure gas is using it quite a bit, not as much here in Anchorage, but it is being used, and then conduit. So it's got a lot of different uses depending on what type of utility or pipe you're trying to replace. And with that, I just want to say, if you guys do have any questions as we go in the room, feel free to raise your hand, because it's easier to answer them sometimes now than later, and I don't mind being interrupted for that. So definitions we're going to kind of go through real quick. So you have static pipe bursting, which is straight up brute force. You take your pipe expander and your product pipe, and you break the old pipe and pull in a new product pipe right behind that bursting head, right behind that expander head. And it's just straight brute force. There's rigs up to 200 tons that can pull this stuff through the ground, and it just physically breaks the old pipe. The pneumatic is similar to a pipe ram type of product. Not as common in Anchorage. It is available, but it's not as common because that's really not used for water pipe. You have to use a continuous pipe. You have to use HDPE, and so if you're using water pipe and you have hydraulic hoses in there, then you have a contaminated pipe. So it's just not as common. I'd say the static is definitely more versatile and used for both systems. Then I talked about the splitting, where you actually split the pipe versus break it. When you have ductile iron pipe that's pretty tough, you can't just burst it. It's not going to break under brute force. You have to cut it and then push it out of the way while you pull the product pipe in. HDPE is the same way. It's too malleable. It can't be burst. So, and then steel as well. I have the others up there from other presentations. There's other different types out there. They're still kind of in their infancy, where they're proprietary. One of them's called Interim, and the other one's called Impactor. Impactor is owned by Hammerhead, and those are specific types of systems that aren't really readily available here, so I didn't really. There's others out there. If you do pipe bursting technology, you'll find them, but these are the kind of the meat and potatoes that's been around since the 80s. So. Manufacturers, I didn't put them all up here, like I said. You got Hammerhead, who actually owns Vermeer and Ditch Witch now. So if you go to the Ditch Witch or Vermeer website and click on their pipe bursting, it'll take you right back to Hammerhead. TT Technologies is the other big guy. Hammerhead and TT are the two big ones that you'll see in all the trade magazines. And then you got UCMC, and each one of their systems, I'll show you here in a minute, is a little bit different. And then Trick Tools is relatively new. They've been around, don't hold me to it, somewhere between 5 and 10 years. They're the ones that are meant for smaller utility sizes, services. So they're around. It's a pretty interesting technology, what they're using, and the size of their footprint is pretty impressive. Any questions so far? So static. We have the static, which I kind of talked about. You have the way it happens is you put your pulling mechanism, whether it's a cable, a chain, or a rod, and rod is the TT Technologies. They have 3 or 4 foot rod sections that link together. You push them down the pipe and you hook it to your hydraulic ram, and it pulls the whole system back into place. That's their kind of proprietary system of how it works. The cable, which is Hammerhead, Vermeer, Ditch Witch, what they do is they send down a steel cable, depending on the size of the equipment they're using, to make sure it doesn't fall apart. Feed it through the pipe, and then pull in the product pipe and the bursting head right behind it. Trick Tools does the same thing. They're the image. Trick Tools is the image right here. They're smaller. What they have is a cable system that has clamps that bite onto that cable, and they don't have the pulling force that the other systems do. They're meant for the 2 to 4 inch size pipes versus the 8, 10, 12s and bigger. They use a hydraulic ram. What happens is that hydraulic ram here, there's clamps here that bite onto the cable, and then the 2 hydraulic rams pull that cable up, and it just pulls 12 inches at a time, pulls a new product pipe in behind. And then the chain system, which is the bottom image, that is UCMC, or the actual company's TTS. That's a gentleman out of Pacific Northwest, and instead of using a rod or a cable, what he uses boat anchor chain to pull through the pipe, and it's just a mechanism for him to get away from the other big guys and have a different type system and still be able to perform the work. Static systems can be used on either fused continuous pipe or segmented. The segmented pipe has to be, or not has to be, but it's generally restrained joint. They do have systems where they can use non-restrained joint pipe. It's not common, and I don't know why you would do that other than if there was a owner preference on a product pipe. But they can use the Hobos or those types of pipes as well, concrete. They can use clay. Really what it does is as they pull it in, they have a clamp on the back that pulls that product pipe, that segmented pipe that's not continuous with it. Again, I can't really think of a really good reason why you'd want to use that. I think you'd rather just use a restrained joint pipe or continuous through your product or through your project. Pneumatic, this is, I touched on it. So what pneumatic is it uses a hydraulic ram, and Hammerhead and TT both have these types of systems, and they use a hydraulic ram that just hammers its way through, and it is assisted, it's actually assisted with a cable winch. So the cable winch is fed through the pipe, the hammer's attached, and it pulls it through with a little bit of tension just to keep it moving, and that pneumatic hammer both breaks the pipe and pulls in the product pipe right behind it. Now this is the one I said where if you use this on a water pipe, it's not really recommended because you've got hydraulic and air hoses that have to be through your new pipe. And so you have this hydraulic hose that's been drugged through the ground and everything else, and it's potentially has hydraulic oil on it. And it's just, you know, it's just a cleaning issue that you aren't going to want to have to deal with when you have a potable water system in the end. In a gravity sewer line, it's not as big an issue, right? And this is the one that is only continuous pipe works on this. You can't use a segmented pipe because you have these hydraulic hoses. If you're going to burst a segment that's 300 feet, you need 350 feet of hydraulic hoses, depending on where your power pack is. That's got to be fed through your pipe to operate it. So again, this is not something that's seen in Alaska very often, but it is out there. So just be aware. Then there's the pipe splitting, and this is really geared. Pipe splitting is first started out with realistically like gas service lines. So this is a small 2-inch line that's pulling in another 3-inch service line, and it could be that the old product pipe was something that the utility owner didn't want to use anymore, that was obsolete. They wanted to update it with new HDP or something. So you got to use a continuous pipe. And again, it's just kind of the same system, but it's splitting the pipe versus breaking it and fracturing it into the ground. It's kind of just a Google search of a splitting head. This is what you're seeing in this image over here. And then this pipe splitting system is a little bit larger. It's meant for splitting old ductile iron or HDP that's larger, 8 to 10 and 12 inch. And these wheels actually increase in size, and they cut and they split that pipe apart. And it can be oriented in the 12 o'clock, 6 o'clock, or all of like 4 cardinal directions, depending on what you're trying to accomplish and what type of pipe you're cutting. And then you have behind that cutter blade, you've cut the pipe, and then you have this expansion. This is just a schematic grabbed off the internet. Your expansion head's actually probably going to be bigger than your splitting head once it's cut, and then your product pipe is behind it. So things to think about in the design. So existing utilities, whether they're known or unknown, and I'll talk about that here in a little bit on the case studies. But knowing where your existing utilities are, both what you have, what you're trying to replace, and what's crossing or adjacent to it, it's pretty critical, especially depending on where you are and what you're crossing. Surface heave. It's really good to estimate what that surface heave. Now the new manual doesn't have the same equations that used to be out there. They realized that those equations were too conservative. I talked to one of the authors about it, and they've got this zone of influence, and it's all depending on how much of an upsize you're doing. And that zone of influence, again, you should get a geotech involved and have them help evaluate that zone of influence. But if you're bursting an 8 to a 10 inch, that's up to 17 inches of zone of influence. So any crossing utilities or adjacent utilities or foundations, you're potentially impacting those. I think the calculations are, may be a little conservative, but we're going to be conservative first, right, as engineers? Because when we start to go from 8 to 12 inch, all of a sudden that zone of influence gets really impressive. that you're actually impacting the soil. It's not just the pipe itself, it's the impact, the zone of influence of the soils. And so this is where you really want to get a geotech involved, know your soil densities, your soil properties, and know what potential impacts you're going to have. Surface settlement, it doesn't seem like that makes sense because you're impacting the soils and you're compressing them. Why would you have surface settlement? Well, it depends on the type of soil you have. If you have a liquefiable type of soil, and then after that goes through, you can actually have a surface settlement. Not as common. It's definitely the surface heave. The image in here shows what a here's a surface heave crack after the pipe bursting's occurred. So you have this little bit of heave, depending on where you are. This is a back alley somewhere in Washington. It may not be the end of the world if you have a little heave, but if you're crossing the interstate, you don't really want that. You now have a speed bump. Think about their temporary system, whether you're doing a water or sewer system. You're going to want to provide services to public utilities. Your customers are going to want to know or be provided that service. They're not going to want to be without water or sewer for more than 6 hours, if you can avoid it. Groundwater. Pipe bursting doesn't typically occur. Groundwater affects how much the soils densify as it's going. It can be completed. There's other, you just need to know where it is and how much it is. Contaminated soils is a big one. We'll talk about that more on later slides. Buildings, I kind of talked about it, where your zone of influence. If you have a foundation footing, you're going to want to know where that is. If you have a basement adjacent to this water or sewer main and you're bursting it, you don't want that wall being affected by it. Vehicles and pedestrians, those are more for traffic control during the project itself. This back alley with these potholes in here, you got this hole here and you got one hole here and here. If anybody's trying to get to their house back there, they're not going to get there for a day or two while you got those excavations open. So just keep that in mind. Of course, the pedestrian traffic, we should be keeping those guys in mind. So new pipe materials, I touched on it. HDP it's what they've been using forever. If owners have put it in, that's what they're used to seeing. My case study will discuss that a little bit. The PVC, C900 PVC, is definitely gaining a lot of traction. Both the fusible, which is a fusible PVC section is here. You can see the long bend radii, and then also the restrained joint, which this is a different system, or this is one of the systems of restrained joint. They hammer those plugs in, and it's a bell and spigot, so your pit and your access pit can be minimized with that. They're using ductile iron in places. I was in Europe last summer and had a picture. This isn't my picture, but they were using this product on a pipe bursting job in Europe. Pretty cool. So they're using a restrained joint ductile iron and then dropping it in their 20 foot. So their pit only has to be 20 foot long, 25, to make sure they have room for the equipment. And then they're using steel. I briefly discussed earlier about they're using concrete, fiberglass, and clay. I put it in there. It's not really common in Alaska, partly because it's not a common pipe material, but it is being done. And depending on where you're working and what your client or your owner wants to use or is in their system, that they may want you to use a concrete or fiberglass type pipe. So that's about it. Any other questions? I'm going to pause for questions. Anybody have questions? James.
So you mentioned geotechnical additional data. Anything different than your typical geotechnical report, such as, you're going to do a different type hammer test, you're going to do penetration tests that are different than just using the hammer or that kind of thing?
So the question is on a geotech, having geotech be so critical, is there something additional geotech that needs to be addressed? I think the answer is what the city of Anchorage is generally obtaining is adequate. You want to know if you have sands, clays, where your water table is, your densities, your spoon tests, that type of information is going to be adequate for most geotechs to help with these recommendations. You want to know what your density of your soil is and what you're trying to burst through. So we're going to talk real quick about some risks. Pipe upsizing. The new manual talks about there's actually class A, B, C, D, and A is size on size. B is going from like an 8 to a 10, C is 8 to 12, and then D is higher. The old manual talked about whether you were doing kind of your bread and butter, your higher risk, and then your developmental type. They had kind of 3 different levels. This one, the new manual talks more about it, and that's where it gets into this zone of influence. I think that's why they did it. So you're upsizing. If you're going from 8 to 8, your risk is relatively minor. I wouldn't say it's non-existent, but it's not moving from an 8-inch pipe to a 12-inch pipe. That's a significant upsize and is going to impact. This is the image here, kind of talks about when you're doing this burst, typically your soils are going to go to the up, or going to compress upwards, because your virgin ground is below you, and it's going to generally be more dense. And that's where there's been projects where it's actually less dense and the pipe falls out, and that's where your settlement happens. So whether depending on your upsizing, will impact this as well as everything around. So, whoops. So this, yeah, you want to know your overburden, your pipe bedding. What was your pipe bed in? If it was bed in a controlled density fill or a concrete encased, you're not going to burst through it very likely. It's going to be a much more risky, you're going to need more equipment or bigger equipment to bust through it. Your soil stability, I kind of talked about that. Existing pipe material. It's great when a record drawing says 5 miles of pipe is all AC, but then you talk to the O&M guys, and they're saying, oh, well, we replaced half of that last year with ductile iron. It's good to know that kind of stuff. So existing pipe material. Unknown fittings, same kind of thing. I like to say that all of our record drawings from 50 years ago show us exactly what we have in the ground, right? Good luck. So they've gone out and done these repairs, and they have bands, and they have ductile fittings, or they have alphas, or they have whatever. So the more you know, the better. I talked about encased pipe. If it's encased in concrete, boy, that's making it tough. Unknown utilities. Boy, if we knew where everything was, it would make everybody's job in the room a lot easier. And then the pipe material change or pipe size changes, those are always things you want to know too. So those are all risks. I'm going to kind of discuss the image here, back to the ABCD. So where you have your connection center point, which is right in the middle, this will adjust depending on what size pipe you're bursting to. So this point, if you go from an 8 to a 10, this is kind of what this image goes. If you go from an 8 to a 12, all of a sudden this connection point's here. If you go 8 to 18, all of a sudden where the bursting rig is trying to pull through is outside of your existing pipe. It's trying to burst through this dimension, and that's where it gets more tricky. That's where your added risks are. Things to consider in your construction documents: access pits, big part. You got to access the pipe. Go ahead.
Yes. What sort of evaluation of the existing piping do you do? You got the TV inspections, or run some sort of a pig through the inspection?
So the question is what type of condition assessment do you do on the existing pipe? And the answer is it depends on whether or not you're doing water or sewer. Sewer is relatively easy. You can send a camera, if a gravity sewer, you can send a CCTV camera down, get those type of information, you know where your service connections are, that type of thing. Water systems are more complicated because it's a pressure pipe. It's more impactful to get in there and open it up and figure out what's going on in there. There is technologies out there, albeit somewhat more cost prohibitive depending on what level you want. So your water lines, generally you go to your record drawings and then maintenance reports. So good question. So access pits, depending on what type of pipe you're fixing, is going to kind of dictate where you go and what type of access pits and where they're going to be. For sewer services, or for sewers, you're going to be accessing at manholes and at the service connections. Unfortunately, this is a technology that once it goes through, you have to reconnect any services. So you're going to be doing more excavations for those type of places, but you've minimized it. So on the sewer side, you're going to be excavating at the manhole, dropping it in. You're trying to minimize that. If there's equipment, that's where the pneumatic is advantageous, where you can drop in the winch and pull to that manhole. And then once the hammer's there, you can take it out and not have to excavate. You don't have to excavate at one pit. You don't have to excavate at both ends. The water is a little more difficult. You're really going to be having a pit at every hydrant because you have a T there. You can't burst through those fittings. Any deflections, any ductile deflections, any pipe upsizing or reducers, you're going to be having you're going to need an excavation there to replace it. Otherwise, it's hit or miss on whether or not a contractor is going to be able to burst through those fittings. And you're going to be replacing the hydrants most likely anyway for your fire coverage. So those are going to be access pits. So now we're going to talk about the case studies, which I think is what probably a lot of the people want to hear about. So, this is a remote site, and that's about all I can say because I didn't get clearance to say anything more. I have some photos of another slide. Limited data gathering. It's expensive to get out there. It's expensive to do any work out there. Mobilizing equipment's tough. All of these things make it really a challenging site. So there's a lot of record drawings, but it's a lot of record drawings. And then this project, there was two projects. It was a design build, which is the DB, and then the design bid build. Those footages were what the contract value was for. As the project went on, it adjusted. It's not quite those footages, but that's what the contract was for. So here's the project area. Nondescript. The yellow lines represent the existing system. That's what the existing system was that had been replaced. So all of this up here had been replaced in the 2000s. And then, including this here. The raw water line, there's an intake gallery here, and it's pumped up to the water treatment plant. The water treatment plant's right under there, right where the blue and the yellow kind of collide. And the design build project, is the red area. And that is where most of the personnel are. That's where the dining facilities, that's where the 24 hours a day operations are. And that's what that is. And then the blue line is the design bid build. That's the approximately 30,000 feet. And to not make it so mesmerizing, I took out all the yellow pipe that's still out there, but not in operation, and it's a pretty wild maze of piping. The facility out there has been around for 50 some odd years. There's been buildings constructed, demolished, so there's just a mishmash of all different types of pipe, utilities, everything, with perfect record drawings. So that's kind of the area. We'll talk more about the project specifically here in a minute. So from the ADEC website, this screen grab, here's your contaminated sites. At one point in space. The owner has their own map that shows the extents of each one of those contaminated sites. If I showed you, it's there, it exists, but all the red triangles are active hot zones. The green ones have been treated, and the yellow are in, well, I shouldn't say treated, they're in cleanup status. And then the yellows are cleanup with institutional controls per the ADEC website. So I didn't overlay the water pipe, but just to kind of give a reference, this is the water treatment plant right here. So the blue lines are all about here, the red lines are here, and then the rest of the yellow lines are just kind of through the island. So, record drawing information. 50 years old, lots of buildings added, demolished, some taken out of service, some recorded, some documented, some not. The record drawings for the area, there's 12,000 of them. So there's a lot of information. And that's everything. That's from buildings, all utilities. But to go through and try to go through it, those that work on AWW systems, be blessed because their system and their GIS is so nice to use compared to other utilities and other areas. Not that this is bad, this is not unexpected, but to try to go through 12,000 drawings is its own effort, you know. So we got what we could and we were able to analyze it, and we used what we were able to use, but it's still just data, and how accurate it is, there's not sure of. So multiple utility crossings, abandoned wastewater, live wastewater, fiber optic, comm, electric, it all exists out there. Some of it's documented, some of it's not. Some of it's well marked on where it is. In other areas, you're absolutely going blind. So, or digging blind. The existing water system, it's 8 and 6 inch pipe. There's nothing larger than that. Correct, Laura? Okay. There is abandoned 16-inch fire protection water line, and I'll talk about that in a second. But everything that's active is currently 8 and 6. It's aged, most of it's AC. It's leaks. They have sections of it isolated. They're struggling. They lose between their entire system. They're losing a lot of water every day, but they're trying to still provide coverage to areas. We have extremely corrosive soils, lots of peats, lots of organics, lots of other stuff in the ground. And then the average depth out there is 3 to 5 feet, not as deep as what's standard in Anchorage, although we do have sections of pipe out there that are 10 and 12 feet deep under inaccessible crossings and that kind of stuff. So most of it is AC pipe. There's some cast iron, some ductile, and that was pretty much it. But most of it's AC. So how remote is it? It's a 3-hour flight from Anchorage. It's more than 2,000 miles from Seattle. So a 10-person jet takes 3 hours. You're not putting stuff on an airplane to send it out there. The barge, rough order of magnitude, every barge is $500 to $1 million just to send a single barge. So your mobilization costs are through the roof. As soon as you can realize any efficiencies in shipping multiple projects together, different materials that weigh less, that are combined, anything you can do pencils out real fast. Yeah, it's way out there. It's not easy to get to. So what we did, our team was brought on in 17 for other projects, but in 2018, we were let the contract for the 2 projects. One was a design build, and we were working for a contractor, and the other was a design bid build where we're working for a consultant, a JV. We're a sub. So in 2018, they hit us up, said, get out there, get your site investigation. And we got out there, took a 3-man crew, spent a week and a half, and gathered as much information as we could. And when you're talking 34,000 feet of pipe, you still don't get it all. You could spend 6 months out there probably and still not get every piece that you need. But it's what they wanted us to do. We sent a surveyor. The contractor for the design build had his own survey. He went out there. I can't remember if he was ahead of us or behind us. Ahead. He was ahead of us by a few weeks. We sent out our surveyor, our teaming surveyor. There was multiple projects they were surveying. They were out there for 3.5 weeks. They were working on other projects as well. And to realize those efficiencies, again, to the high mobilization costs, they were picking up all the other projects that we needed to pick up. So it was, when we were out there the first week and a half with them, helping them. We were kind of working ahead of them, finding the valves, identifying them, talking to them at night, saying, hey, this is where we worked, giving them the updated base map, and then they were working with it out there. So it was a really interesting project, a part of the project. So then once we got all this information, we had the design build contractor with the survey, we had our survey, and we had GIS from the owner. And we were trying to merge all of this. We spent a month and a half between the different databases. There's the survey control discrepancies. Again, it goes back to the utility record drawings, and trying to merge it all was not as fluid and seamless as what we had hoped it would be. But in the end, the owner wanted this entire map of what their system is out there of all the utilities. So that was one of our tasks. And then we didn't do the geotech, and that was partly because of the cost of the mobilization. And again, all of the historical knowledge of what had been going on out at this facility for so many years. We had a really good idea what's going on with the soils, between the contaminated investigations, between all the projects, between the record drawings, the geo bores on all the stuff. We really had a pretty decent idea for the water that we didn't feel like we needed to gather that additional geotech. And so when the owner said that they didn't want us to do it, well, it was against our original recommendation. After talking through it and gathering that additional information, it was kind of like, you know what, you're right. We think we can have a pretty decent design without this additional information. So the photos here, this was our site investigation. I shouldn't even say most, about half of the valves are in pits, and these are the valves in that pit. And most of them didn't have the sand and gravel in it, but just to kind of give an idea of what we're working around. And then this here's the surveyor picking up all of his information. This is an old CMP culvert, or not an old, it's a CMP culvert turned vertical, and that's your vault. But then there's other places where the valves weren't, they were direct buried, which is what my experience is more standard. So to have all of our valves and PRV needs to be in a vault, but all of our valves and bends and flanges, they all wanted them in vaults. And we worked with the owner early to talk through what that was going to look like in the end if you wanted to put those back in, because that was going to be pricey. Any questions so far? Any other questions? Okay. So what did we do? In the design build, both these contracts were awarded in October, November timeframe of 2018. So we were out there right away on our site visit. And the design build, with the design build contractor, the owner had those yellow pipes previously, those had been installed with pipe bursting. So the owner was really comfortable with pipe bursting. It was done in the early 2000s, mid 2000s, was familiar with it, liked it, was comfortable, wanted us to do that to minimize the soil excavations so we didn't have all the contaminated soil excavations. So there was some discussions back and forth. In the design build, we've been told to do pipe bursting, period, use HDPE, period. Okay? There was actually quite a few discussions back and forth. That's how it all shook out in the end. It's all HDPE up there, using pipe bursting. But with the design bid build, what most of the people in the room and the faces that I see, that's kind of more our comfort. That's how we normally do our projects. We had the opportunity to do a kind of initial study and make recommendations on what your alternatives are. So we looked at CIPP, cured in place pipe. Is this something you guys want to look at? It's relatively specialized, but there's advantages to it. Do we want to look at it? Do we want to look at slip lining? I talked about the 16-inch on the southern portion of the island, right next to the water line, the 8-inch water line. There's a 16-inch that was installed for fire protection. Long straight runs. We offered to them, hey, you could do a slip lining here, realize the benefits of not having to provide temporary water. We can put a new pipe inside the old pipe, grout it in place. You might realize some real cost savings. Talk to the owner client, and they said, that's viable, but we still want to stick with pipe bursting because we can deal with the temporary water issues. We don't want to, in case we ever do have to go back and dig in, we don't want to be cutting through the grout and dealing with that type of stuff. Okay, so we did offer it, but it ultimately ended up in a complete pipe bursting design. And then this is where the class A and B, the design build was a class, it was a class B because we went from 8-inch to 10-inch. And then in the design bid build, we have 8 to 8 because we did do some PVC. I'll talk about that in a second. And then we also went 6 to 8 and 8 to 10. So we have class A and B in the design bid build, and that's just impacting the actual zone of influence. So pipe material selection. HDPE for the design build. That's how it was decided. For the design bid build, knowing that we were going through some of these petroleum contaminated areas, the risk of using HDPE in these areas, it's not just risk, it's just not recommended, period. So through the early stages of design, we recommended, and they don't want to use metallic pipe out there, too corrosive of soil. While it's a better product for contaminated areas, they didn't want to do it. Fine. So our recommendation is to use petroleum resistant gaskets in PVC, which is kind of what your upper right photo is showing. It's a bell and spigot. They use a spline, or the other photo I had where they put the little knobs in and they hammer it in with a hammer. Either one of those systems is acceptable. They were really resistant, or not, they were hesitant to use PVC for the, stigma is probably not the right word, but the concern that it's fractured, or it's a more fracturable pipe, it's brittle. Even though C900 is not, it's still that, it was still just a concern for them, as well as they're putting in HDPE. They wanted uniform pipe materials, but you just really can't use the HDPE in petroleum soil. Through the design process, we use those contaminated site maps, and we identified where the known contaminated sites are. We incorporated in the design to take out extra petroleum resistant pipe materials so that it's on site. If they find unknown contaminated sites, they have a mechanism to still have pipe out there. Again, to ship out 29,000 feet of pipe, if you only have 29,000 feet and you have to switch out 1,000, that's really expensive. So it's all part of the bid process. So that's what we did. Is we have both on the design bid build. We have both HDPE and PVC. I want to say, yeah, so I have 19,000 feet of HDPE and 10,000 feet of PVCs in the current design. And in that, I talked about it. In the contaminated areas, the known contaminated areas, we use C900 PVC and then HDP in non-contaminated areas. And we took that map and we offset everything by 50 feet. And to try to make sure that where this transition, this isn't a super elaborate detail, but just to kind of give an idea of what. This is the HDPE side. We're using a reducer, just a ductile iron fusion bonded epoxy reducer with megalugs to connect into the PV. This is the PVC side. So we go from 10-inch HDPE to 8-inch PVC, and we didn't call out the petroleum resistant gasket here just for a cost savings, but this is supposed to be outside the contaminated site anyway, so it wasn't as big a concern. And we had the owner's environmental group on side, and this is what was all decided up front. So this is just we had about a dozen of these, I think, in the total project. Originally, through some of the processes, we had triple that, trying to go from HDP to PVC to try to really maximize the HDPE versus PVC. Temporary water, the design build project, because we were working for a contractor, they were on site. They approached us to be on their team. They had the plumbing and the knowledge of what was going on out there. They were more responsible for the temporary water, although they did rely on us to help them through what that meant with the phasing to make sure that it was able to be accomplished, because again, this is the area where people are living 24/7. We really wanted to minimize any outages. On the design bid build, we met with the users and owner, part of the site visit, found that information, tried to incorporate those needs into the design so a contractor can bid on it, create a bid ready or a biddable requirement. We did through that. Through the design process, there was 10 sequences identified. I'll show you here in a slide of the one that was most critical that we added or made sure it was clear in the documents that the contractor go fix this one first so that the rest of the system can kind of be up and running. That was something we wanted to make sure. I've already talked about this. The potential zone of influence on the design build, and I actually had that wrong. On the Class B is 36, no, I take that back. It was 17 inches. And then from going on the design bid build, we had areas of up to 36 inches. So from our old pipe, we had 3 feet that the soil would be impacted. Now it's not linear. It's most impactful right next to the pipe, and by the time you get to that 36 inches, that's pretty well minimized. But that was the calculations we did. So now the construction photos. This is kind of showing the fusion setup. They originally had the McElroy fusion machine out in the weather. It's a marine environment, doesn't work well. It's very windy, very rainy. They quickly decided to put it inside a Connex and be able to do their HDP fusion here. And these are all photos from the design build, because the design bid build has not been constructed yet. Here's kind of just an idea of your general site conditions. Here's your product pipe, an existing utility that's not supposed to be that shape, but it was hit with the excavator. I think they never told me. This was an unknown utility. One more unknown utility. It's not from the pipe bursting process. Just want to throw that caveat out there. The contractor with UCMC, so this is their diesel generator that powers the hydraulic rams. Whoops, sorry. So this is the power plant. And then they run hydraulic hoses down here. There's 2 hydraulic rams that just push against this plate and pull this chain through the old pipe. This is here's your anchor chain. This is a here that was probably for a hydrant or a bend, and they had to excavate it out. So you can see the chain going through. So depth of pipe, kind of give you an idea. I was not on site. But, this guy's squatting, and he's not much below the ground surface. This is not a typical pit that you'd see in Anchorage. Question.
Where's this contractor based? These two contractors? Was it one contractor?
This is the prime was Bryce Environmental Services here in Anchorage. Yeah, well, one of their many companies, one of the many Bryce companies. Oh, sorry. The question was, is where are these contractors based? Bryce was the prime, Bryce Environmental Services, and then UCMC was the subcontractor that did the pipe bursting. They're from Washington. So this photo was just to show the depth of pipe, relatively shallow. There's other deeper areas, and then the photo on the bottom left is to show, a casting of the thrust block and then the field applied coating. That's a Viscotac product, and that's what in our design build phase we recommended that they coat. The owner was really hesitant to put any metal in the ground. Well, it still requires, unless if you have a vault at every one of these, which is really cost prohibitive out in this more than 2,000 miles away barge shipment to add all these vaults. Not that it couldn't be done, but it was just very expensive. We recommended sealing off all metal parts and fittings with that Viscotac product. So, again, so the original design, again, trying to avoid the metal fittings, they wanted to use electrofusion couplings. And through a lot of discussions with them, talking to different owners, utilities, everything, it was accepted as a connection point. In some discussions with the contractor, so there were some recommendations. Hey, you may want to have some other options. You might want to have something that allows you a little bit of flexibility, that you can do the connection from HDP to HDP. So we told them, we recommended that they take some Romac alphas out there. And needless to say, they were very grateful for that recommendation, because this helped them do these connection fittings where things weren't perfectly aligned, and HDP and tension trying to do an electrofusion. It's just, you've increased a lot of risk. It's not that it's not doable, it's that you've increased a lot of risk. So we had a lot of different fittings out there. This is a hydrant leg here that didn't stay. The cinder blocks didn't remain in place. It was just a temporary hold while they were doing their assembly. So this is a pre and post construction photo. This was a vault. Again, in some of the areas they had a lot of their valves in vaults. This was existing HDP. This was one of the bursting jobs that happened in 2000. And then our project was to go through and replace all of this. So this is generally in the same orientation, HDP that was burst through with the tracer wire, new valve, all flanged, new fittings, all fusion bonded epoxy, trying to avoid this surface corrosion. Again, an alpha, Romac alpha here to do the connection. The design actually had that alpha on the outside of the vault wall, but they were able to make it fit inside. No skin off it doesn't affect me one way or the other, but they have access to their legs and stuff here now. Generally the same orientation, looking northwest. This was, so what we have these post indicator valves out there. We have subsurface valves. So again, this is a buried valve. And so when they would say, well, we put all of our valves in vaults, and we'd kind of go, are you sure? I don't know if that's entirely, so where this was, and then we put a new hydrant, new valving, the water line, the water main runs this way, and just kind of give you an idea of what was pre and post. So now the design bid build. Took that screen grab. The blue line is our design bid build, about 30,000, 29,000 when it was all said and done. The most critical section. So you get right now the system is offering about 20 PSI of pressure down here due to leaks, due to valving, even though this is higher in elevation than here, but their system is failing. So from here, they're putting out 80 PSI. There's a PRV up here. This feeds it. This is this leg here is a back feed. This segment right here is shut off right now. And these facilities are all being fed through this one pipe that is only providing 20 PSI at a hydrant down here. So we told the contractor, Mr. Contractor, when you bid this, fix this segment first. And it's not exact representation, but get this looped up so that then they have water feeding from both sides. Good idea, right? I mean, what goes along here may need some fire protection down here. So let's get the hydrants up and running. First and foremost, let's get going on this. So that was the only stipulation we had on which one had to be constructed first. The remaining 9, we left it to the contractor. We made our recommendations, but we fully anticipate that they may say, you know what, we're going to do this one first, and then we're going to go. Our guys are ready to go from here to here. We're going to do this one next. Oh, fine, let's talk about it, but get this one done first so that there's water duplicate, so it's looped, so it's not just being fed down this one that's not acting correctly. You know, it's not providing the water service. One of the other additions we did because of the record drawings and not being able to get all the information on where all the fittings are and all the old abandoned hydrants because they've knocked some down and buried over them and all that stuff, we showed in the drawings where we anticipate those access pits to be located, but they may not be. Our design, we fully anticipate you're going to dig a pit at the hydrant T and the next hydrant T, and you're going to burst between there. But before you do that, take a CCTV, a closed circuit television camera, similar to what you're using in the sewers, and TV that line. Let's find out where those fittings are, where the extra bands may be, where a pipe material change may be, so that if an intermediate pit has to be constructed, we'd much rather do that prior to the burst than have a burst go and they get stopped and not know where it is. Let's work with the contractor so they have pay items in their bid item to do that CCTV. And we talked to the owner early, said, you know, because of the unknowns here, we really recommend doing this it's going to be a little bit of cost, but I think we are pretty confident it's going to save you money in the long run. And working with the contractor and giving them so that they aren't out there just flying blind and bursting and they're halfway there and that rig stops. Why is it stopped? How do we know? Now you have, do you just dig down and find it? It might be somewhere that you didn't want to dig. Let's find out first, and then if we have to address that through the design or through construction change orders, we can at least do it. We can meet at the table. The other thing we did, the temporary water, especially down there at the southeast end, it was part of, we did provide temporary water designs and requirements to make sure that that was there. The design build contractor, when he did his work, he was actually able to phase it correctly in a way that he never had to set up temporary water. Again, that was his local area knowledge, able to do that, perform that work with the owner, work with the users of the buildings, and be able to do that where the kitchen's open 24 hours a day, but they were able to stage it and, you know, be able to work on a weekend where there's fewer people and get that done. Question?
How many people are on that base? Roughly?
Question is, how many people are out there? There's about 100 to 150 people in that range. So, yeah.
Not saying it was a base.
Not saying what it was. That area, that site. Yeah, so it's a lot of work, a lot of pipe for 100 to 150 people. The other, like I said before, we didn't show all the existing yellow utility lines because it's a maze of pipe. So we removed, part of the design was to remove those unnecessary segments, tried to consolidate. Just real quick, so there was an extra loop in here and an extra loop over here. We consolidated and looped. This is actually an open cut right here, just to try to reduce that need for having the duplicate pipes. Try to make it more efficient. So, and then one of the owner wasn't used to seeing this, the bottom schematic, giving them what parts and pieces. This is we did this for every one of our connections. So there's 4 pages at the back that just have schematics. And it's easier for the contractor to go through, take his bill of materials off of this without it putting the onus on the designer to do it. Here's our schematic. You may change it. You may decide to, instead of doing from, you may cut this out, Mr. Contractor, and you may go from here to here, depending on the site. But at least it gives him a bill of materials that he can order and bid against other contractors with. And so we did this with the design build project. That contractor hadn't really seen that before in the fee negotiation. It was kind of, do you really need to do that? Trust me, yes. Because it's going to help everybody between the inspectors on site, you and us, when we go back and we're looking at figure A, and we can say, well, this hydrant moved 50 feet east, and so we had to change these fittings. Okay, got it. Makes sense. So highly recommend doing those. You know, I know AWW, all their designs lately, they're putting these in, depending on your owner and where it is, or what they want to have in their product. I think it's a great thing to have in your record drawings. And then requiring your contractor to mark them up is also a good thing to do. Any changes they make, right? It's constructed just as designed. So I'm just going to quickly talk about the contracting mechanisms. The design build, it was a quick project. We got under contract in October, late October, early November, and it was constructed in 10 months. And they did 4,000 feet of pipe. Different set of deliverables. When you go to the design bid build, you have multiple reviews with your owners. We had it with the design build, but not to that same level. The design bid build was finished in November last year, November, December, and the equipment's not going to make the barge, so they haven't advertised it for contractor bid yet. They anticipate late summer this year for next year's barge, so it's going to be probably a 2021 construction, unless if a contractor the contractor that's out there decides to, he puts in, wins it, and he might start working this fall, winter. But that's kind of the schedule. And the advantages and disadvantages, I don't want to take it. I want to make sure there's enough time for questions at the end, and if you want to ask about it, that's one. So quick takeaways: perform those calculations as part of your design. Depending on the client and what they want in the end, they may require those calculations. So get them figured out. Meet with your owner, the client frequently, making sure that whatever contract mechanism you're under is you're providing them what they expect. Again, this goes back to pipe materials, making sure you're not going down a design and providing something that then they don't approve. Your optimal methodology, that is it's hard to determine your true optimal methodology. It goes back to contractor means and methods. Let them sometimes have a different idea. When you can do a pneumatic and then a contractor may say static and I've got it and I can do it for half the price. Let's talk. Let's talk through it and see if that makes sense. New pipe material, make sure you're providing the one that's going to meet the site conditions that you need and the owner's expectations. The pull force requirements, those calculations have changed in the third edition. Again, this kind of goes back to a means and methods and having the contractor interpret the soils information. Generally speaking, they're pretty good. They know what you need, though. Make sure you're not going to pull your pipe apart. Evaluate your site constraints. What do you have? What crossings do you have? What site utilities? What are you trying to avoid? And then mitigate your risk as best you can. There's no way to cut out all risk, but the more information you give to a contractor, the better bid price they should give you, and telling them what their limitations are. And with that, I'm going to open it up to questions. So, James.
So you used Viscotac on all the buried fittings, but I saw on the valve vault you didn't use any there, or did you decide to coat in the vaults themselves?
The question is we used the field applied coating in the buried areas, and in the vaults there, the photo didn't show any. And I got to be honest, I don't know what the final determination. Some of those photos were taken during construction, but I don't think they took enough field applied coating out there.
But
So
was it planned for coating those because of the high salt, ocean environment?
no, yes, it was in the discussions in the design build. The design bid build documents, all metal fittings are going to have a field applied coating. Good question.
You mentioned a manual and additions. What's the name of that?
It's the NASTT Good Pipeline Good Practicing. I can go back. I have the title of it in that one slide. That one there. Sorry, the question was what was the manual? It's right there at the bottom of the screen. Any other questions? Yeah.
In the design build, did you tell them exactly to use HDPE pipe or PVC? Were you specific on that? Or did you allow them to, you said you were doing
The question is on the design build, what was our input on pipe material, right? In the design build, we were We were told to use HDPE.
Sort of a bridging document here, some of the scope.
Yeah, there in the design build, was it a bridge? What is a bridging document? Is the question. And in the design build, early in the project, we sat down with the contractor, the owner, the client, and the users, and us, and gave our recommendations. And that their contaminated areas that they know of is a little bit different than the ADECs. So, and there we met with their environmental group and had multiple meetings, right? Yeah, 3 or 4 meetings discussing it and just identifying the risks and letting them know. They had to do visual, odor, while they were out there. If they found it, notify. I didn't get a phone call. I'm stating the facts,
No news is good news.
yeah.
What order of magnitude was this?
Thank you.
I don't know if I can. The design build. Well, the design build was 3 projects together. It wasn't just the water line. There was also a sewer lift station and some airfield lighting. So I know that dollar value, but I don't know what that is. And the program amount for the design bid build, it's big. Yeah, it's very costly.
Your pipe materials aren't what driving that.
No. Pipe materials it was not even, there was many discussions. Well, what's the pipe material cost between the two? Insignificant. The question was, what was the pipe material cost? Yeah.
Just out of curiosity, what's the source of water?
Question is, what's the source of water for the drinking water?
Yeah.
So, it's all surface water. Whoops, wrong button. There is a drainage basin that generally slopes. It slopes from north to south, and the basin is this area. And it drains to infiltration gallery here, and there's a pump house that pumps this. My schematic isn't perfect, sorry. There's a pipe that runs from this pump house to that, and then it pumps up the hill. So it's all surface water.
So if there's an infiltration, what about concerns for contamination?
I can get you the contact number for the environmental person if you'd like it.
There's a water treatment plant.
But they test it there. I mean, you can go to the DC website and see what their treatment results are and all that stuff. It exists. It's not hidden. I don't want to say. I don't know well enough.
You showed that duct pipe that had blue coating. Is that a unique coating for driving through or preventing against scratches?
I stole that picture. I don't know. The question is the ductile iron, when I was in Europe, that's what their pipe's coated with. It's not what we see in the United States. It's not that it probably couldn't be purchased. It's probably very expensive, but that's just a screen grab from the internet. The screen grab was more for the gasket, the restrained joint gasket, not the coating.
No more
Anything?
questions? So please join me in thanking.
Thank you.